First, we have two local nodes running here. On the left, we have Clayton local node. On the right, we have an Ethereum local node. Second, here, this is ChainsAtlas Arena, which is our integrated development environment, allowing the user to easily interact and execute code on ChainsAtlas virtualization units. Virtualization units are smart contracts deployed on the chosen blockchains. If we go to this tree, we're going to see the connected blockchains. Currently, we are running two local nodes of Ethereum and Clayton, so they are connected to this IDE. Next step, we need to deploy virtualization units. Virtualization units are smart contracts deployed on the various supported blockchains, and these smart contracts do the virtualization. Therefore, the smart contract virtual machine itself, the smart contracts itself, executes code on top of it. So we're going to deploy to Ethereum, and we're going to deploy it to Clayton. The user can deploy multiple virtualization units on each of the blockchains. Doesn't need to be one, but for this demo, we will just put one. Going back, as you can see, we have the virtualization units connected to these, the ones deployed. Next step, we're going to take an example of code, C code, here. As you can see, this is a maze solving code. It has a recursion. It's a standard C code. There is no adjustment needed for the blockchain. Exactly copy paste as it is. So now we're gonna click here. This is a UI illustration of the output of this one. But this algorithm, while it's running, it will show output here. There will be the memory and register. Memory and registers are the state of the virtualization unit, are the information that while processing the smart contract, our virtualization unit, are the state of the smart contracts. So first step would be, after passing the code, we can just execute it on a given blockchain, or we can define a strategy. A strategy allows you to execute on various blockchains synchronously, and sequentially, or asynchronously in parallel. So for instance, we want to, if the algorithm computes solves this maze, it will determine a set of steps to get out of this maze from A to Z. And what we're gonna do is we're gonna instruct the IDE to tell the ChainsAtlas network, when running this algorithm, only run a part of it on blockchain A, and then jump the execution to blockchain B. But when you jump, it will continue exactly where the previous blockchain finished. So it will save state. This is exactly similar to the case when you are running a virtual machine on your computer. You pause the state, you shut down your computer, you turn your computer back, and you turn on the virtual machine from the same state, and all your applications that you are running, they continue exactly where they were. So we're gonna say the first part will execute on Ethereum, and the second part we're gonna execute on Clayton. And we're gonna say at step 3000, jump the execution from here and continue here. So this is a simplified example of a strategy. Click on run. As you can see, it's Ethereum. There is the output that's supported, and then you're gonna switch to Clayton. Now, by examining the output, we're gonna notice that Ethereum, the execution, the part that was executed in Ethereum, executed this part, location 11212232. But once the transfer happened to Clayton, it continued exactly where it was, where Ethereum finished. So it continued from 32 to 33, 43, and so on and so forth. Now we're going to take a closer look to what's actually happening. So for that, we're going to use Ganache because the logs are easy to read and observe. We're going to stop the local node of Ethereum, and we're going to run a Ganache. We're going to use Node and Web3 to interact with it. This is an example of the code. So this part here, the Sol core, is our smart contract visualization unit. Again, as stated earlier, the smart contract is the virtual machine, our smart contract. So we're gonna compile it and deploy it to the Ganache. And until line 44, we will get the contract instance with the address and so on. So we're gonna create a contract instance. After we deployed all of this part is for compiling and deploying the virtualization units on the chosen blockchain. And once we do that, we take a C code, we compile it, and we send that the bytecode, which is the output of the compilation process. The compiler is a client-side application. So this software will compile the C code, will provide a bytecode. That bytecode is then sent to the smart contract, the virtualization unit, and executed. And then we can get the output, bytecode output, or the byte output, which is the output of the execution of the sent bytecode, and we can print the results after decoding them. So we're gonna execute the first part. Here it's compiling the virtualization unit, then it was sent. As we can see, we have the logs that support that. Now we're gonna take this part, this input C. Let's take a look what's the content. It's this one here. It's a simple C code that does an iteration and print from 0 to 4. So we can take a look actually over its content. Let's go to the same path. 16-bit input.c. This is the content of the file. It's the same one. This is the one. So what we're gonna do, we're gonna take it. We're gonna just do the compilation now. Let's take a look. So the compilation gives us a bytecode. Let's print it. So this is the bytecode. Bytecode is the compiled code of a C code to an architecture that the virtualization unit or our smart contract would be able to interpret. Now we're gonna send it and print the results. Here is the return. Here is the call. This is the bytecode. As you can see, these are the results. Iteration 0, iteration 1, 2, 4, exactly what this function does if executed in any computer. So, thank you.